a professor at the University of Concordia, Canada. His research interests are structural dynamics, earthquake engineering, structural health monitoring, infrastructure rehabilitation, and finite and boundary element methods. He has received a number of prestigious awards such as NSERC Postdoctoral Fellowship and ISIS Canada Postdoctoral Fellowship. He has also received ENCS Teaching Excellence Award. He is a licensed professional engineer in Ontario and is affiliated to CSE, ASE, CAE, and ISHMI. He is currently a fellow of the Canadian Society for Civil Engineers. He has authored more than 100 articles in reputed technical journals and conferences. He holds 2 patent applications and a number of technical reports for academia and research and industry. They have also been written by him. He has delivered several keynote and invited lectures in several international and national conferences. So we had the privilege of meeting him personally during his last visit. So let's welcome Professor BAGCHI. And now Professor BAGCHI, he will read out his presentation lessons from SHM of Infrastructure in Canada.
Thank you very much for the introduction, and good morning or good evening to everybody. Morning in my time here. So it is a little bit cold. It's snowy, but beautiful morning, sunny. So I hope you can see the change of slides, right? We have off downtown campus in summertime. At the bottom, we have downtown campus in summertime. And on the right, we have the campus in wintertime. So wintertime is mostly snow-covered. Snow gets melted away from time to time, but generally it remains snowy. So today's presentation, I tried to focus on SHM activities in Canada. So to start with, I just want to remind you about the current state of our infrastructure. I mean, global infrastructure, not just in Canada. So Canada, US, Europe, in these countries, a lot of infrastructure were developed during right after the World War, Second World War. And many of them are in really bad shape because many of them are at the end of their lives, and some of them are demolished and reconstructed. Those that are still in operation, most of them are quite old. So that brings the urgency of rehabilitating them, monitoring them, making them in good shape until a new infrastructure is built. You know, in concrete structure, corrosion is a very important or very harmful aspects that we encounter all over the world, depending on the weather. In Canada, although it is cold country, but many a times because of the fluctuation in temperature, the snow cleaning operations and all these things can create stress on this kind of structure, which accelerates corrosion. So when we rehabilitate these structures, we use many a times, modern materials along with the older materials. We use innovative constructs or structures. But to maintain these structures, monitoring is important. So in Canada, they tried different type of innovation in structural rehabilitation or creating new structures. For example, we are using FRP materials, fiber reinforced polymer materials, early on, while developing. There was no code or anything. Then they started developing the code and started using it on a regular basis. Then there is another kind of bridge construction they started doing, which is called steel-free deck. Steel-free deck is basically, as the name indicates, we don't use any steel internally, which it means that uh, it's not fully FRP reinforced or polymer reinforced concrete. It is still concrete, but we, instead of using steel bar externally, a steel plate is used externally to promote arching action in the bridge deck. For example, in this bridge deck, there is a girder, steel girder here and here, and there is a steel plate connecting them. So when there is a load coming from top, it tries to push these girders away, and that creates arching action. And concrete is good in taking compression. So that's how it takes the compressive force. Then other kind of structure they use, like filament winding. I'm not going into details with this. So FRP materials became quite popular, but durability of FRP material was not well known at that time, because it is about 20 years ago they started. But the attraction was it was lightweight, high strength, corrosion resistant, and versatile. So that's why most of those bridges, wherever they used FRP or steel-free deck or any kind of innovation, they instrumented them. So these are some of the applications for FRP where they used it for flexural strengthening. Now it is well known. Many of the countries have adopted them. At that time, it was evolving. So they are developing different, layouts, different design process, etc., for shear, confinement, etc. Now, what do we do? Why we need monitoring? So we know that structure deteriorates over time, and exposes its deficiency, and also many a times it encounters excess demand. For example, some of the bridges which were developed or designed for certain level of load now has a higher load demand because traffic increased, congestion increased, or speed limit increased. So that increased the demand on the structure. Now, when the demand on the structure increases, durability of the structure will get affected, performance of the structure will get affected. When the environmental effect, like aging, freeze thaw, moisture, etc., attacks the structure, or structure is exposed to those things on a continual basis, their capacity reduces. So we need to know what is going on in the structure so that we can maintain it regularly. So that's why evaluation of a structure is very important. And we all know this. I'm just, recapping this. So this slide essentially says that when we are using innovative materials, or we want to know the behavior of the structure, I'll give you an example. Say you repair a structure with a certain kind of solution, which is not standard. So you make some design assumptions or things like that. Then we need to ascertain that design assumptions were right. So in that case, the only way to know is by instrumenting the structure and monitoring its performance over time. So we need to understand the behavior, prove the design concept, any design concept we adopt, then detect possible damage or degradation. This is sort of a regular objective in any structural health monitoring. And then another important aspect is estimate remaining service life. Why do we need to do that? Say I have a bridge which is built for, say, 40-year period. The design life is 40 years. When I monitor and look at its performance, maybe after 10 years, it starts showing some distress. Okay. So I do repair. So it enhances its performance and life, but it still deteriorates. So we need to estimate how long I can go on like this until I make a decision as a owner, if I am the owner, when to replace this bridge. Okay, that's why assessing the service life is important, right? I mean, before, if you don't have monitoring, what consultants do normally, they look at the bridge, see if it is in good condition or not, like if there is, spalling, exposed rebars, etc. They say, you tear down the bridge and reconstruct. It is good for the consultant because it creates a new project. But if you really analyze and assess the bridge, you might find that the bridge could go for another 10 to 15 years. Now, if you can lengthen the service life by monitoring, it saves money in the longer term and you can focus on more important projects. So that is the importance of structural health monitoring. Sometimes we need to estimate the external loads. External loads are not easy to estimate, and many of the bridges implement something called weigh in motion, where they weigh the passing vehicles, trucks, heavy vehicles, etc., and see how much load is coming on the structure. But through structural health monitoring, can we do that? It essentially generates an inverse problem where the solution is known, that means displacement is known, but the load is not known. So it creates its own challenge. I think most of you know what is the analogy between human health and structural health. Like in human health care, we take help of different diagnostic measures. We see professionals, health professionals, doctors, and based on different tests, they give us a prescription, right? So similarly for SHM, we monitor the structure, measure different performance or response characteristics, and based on that, the engineer diagnoses the condition of the structure and prescribes remedial measures. This is the typical layout of a structural health monitoring system where you have sensors from where the data is collected, managed and archived. Then system identification is done. I'll talk about system identification. What is that in a later slide? And then sometimes we build finite element model, correlate the structure, and interpret the data and structural condition based on what we have from the field. There are different methods, traditional methods. I put visual inspection as an inspection method. It is also monitoring method, right? Although it is not instrumental. But visual inspection gives us some cues, what is going on in this structure. This is traditional method. It is not complete by any means. That's why we need instrumental measurement. So we carry different equipments in the field, like ultrasonic devices, acoustic devices, and test the structure. Okay. Sometimes we do load test by putting a truck with standard weight and do static field test. Okay, and collect data. Many times we do dynamic test. Okay, that means we take ambient vibration or forced vibration test and collect the data from that. So these are all called periodic tests. And then we come in the realm of continuous monitoring. So continuous monitoring is where we put the data, put the sensors in the structure permanently and continuously access the data and evaluate the structural condition based on that. Okay, I'll not talk too much about this, but the data management is one of the major issue in SHM, because many of the structures, especially in North America, they are instrumented and they collect a lot of data every year, every hour, I would say, not every year, just every hour. But they don't put as much effort on assessing the data. They only do the key assessment and leave it there. But data could show a lot of information about the structure. I think this is a worldwide problem. And structural engineers, civil engineers, they do whatever they can do, but I think there is an enormous opportunity for collaboration with other professionals like data scientists, computer scientists here, that can help in categorization of the data, categorization of the damage categories, identify trigger points, okay, and reduce the volume of the data by discarding what is not necessary. So I was talking about system identification a while ago. System identification is very important aspect of monitoring a structure. So suppose I have a bridge, I want to know its characteristics. So characteristics means what? I want to know its stiffness, for example. I need to know its mass, um, frequencies, etc. Now, in the field, it is difficult to measure. So we can take the structural health monitoring information and indirectly assess them. And that process is called system identification. There are many different ways depending on what parameter we want to assess. Then another important use of structural health monitoring is structural model update. Okay, what does that mean? Suppose I have a finite element model of a bridge. I followed all as-built data. I used everything and analyzed the bridge. And then when I go in the field, look at the structural health monitoring data, do the system identification to find out what are these quantities. Okay, also damping. I see that whatever my finite element method is giving, FEM versus real, they are not matching. So what do we do in that case? We need to update the finite element model to correspond to the real structure. Okay. It can be done manually if the structure is simple and model is simple. But if the structure is complex and the model is complex, then we need to use some mathematical technique called structural model updating techniques. And there are many methods. Monitoring external events like, earthquake, heavy vehicles, cyclone, heavy wind, all these things are natural phenomena, right? Heavy vehicle may not be natural, but we can call it natural because, structure, we don't have any control as such on the traffic much, except few traffic control measures. So we need to monitor the structural behavior on that because, if we design a structure for a certain level of earthquake, and if similar kind of earthquake or even a lower level of earthquake happen to the structure, if the structure is instrumented, we would know that how the structure behaved in that event, whether our design assumptions were right or not, whether I need to do any retrofit for this structure. Okay, that's very important. For bridges, they always use traffic control measures based on the condition of the bridge. Okay. So vibration monitoring is a very important technique we normally use. It is not a continuous process, it's a periodic monitoring. So what we do, we take our instruments like vibration measurement instruments like accelerometer, velocity meter, etc., instrument the structure temporarily and excite the structure. Okay, how do we excite the structure? Sometimes we put some kind of mechanical shakers on the structure, or if there is natural way of vibrating the structure called ambient vibration, then we take those signals. And based on that, we figure out what are the system properties. And also, if we do it on a regular basis, say every year or every 6 months, that will allow us to find the difference in behavior from one stage to another stage and help us localize the damage. Okay. So this is an important aspect. Localize the damage based on global quantities. If we know the damage in a local area, we can do local tests like ultrasonic test or ground penetrating radar or whatever we need. But if we don't know locally, then this provides a global method to identify the areas where there could be a problem. And then we can send our team to do local estimates or local measurements. And that way it becomes very cost effective. So vibration-based damage identification is based on that concept that we uh, we measure the structure at different stages in time, say T1, T2, T3, etc. And then we take one of the condition as baseline and then compare the structural response at another time and use the vibration properties like mode shape, frequencies, or their uh, you know ancillary parameters based on them to figure out what are the damage or any kind of condition change that has happened in the structure. It is not only for damage. Sometimes we use this to identify if there is any problem with the sensing system itself. So, I mean, that is the just the basic information. I'll give you some examples from Canadian implementation of SHM systems. This is one of the bridges that was constructed with that steel-free deck concept. Steel-free deck concept means there are external girders which are tied with external steel plates, and there is no internal reinforcement in the deck. No internal reinforcement. So when you apply load, the small cracks develop here, and this pushes these girders away. So when the girders are pushed away, tension develops in this steel bar. Okay, that way it creates some kind of an arching action. So where the concrete is in compression and steel plate is in tension, and that's how it takes the load. The time when they constructed this bridge, there was no code for this kind of bridge. Code, in fact, did not allow. Okay. But Canadian code has some mechanism. It says that if you apply any kind of new technique, then you have to prove that it does better than the conventional design. Okay. So that's why they instrumented this bridge at that time. And we are talking about 91 to 95 in that period. And try to demonstrate the structure, performance of the structure. So from time to time, they measured what is the load distribution in the structure. They did static load test, vibration test, and all these things. I'm not going too much into detail, but that experience was very valuable. Okay. So based on that experience, they constructed many other bridges in Canada and some in the US. Okay. And of course, design evolved a little bit over time. It got included in the code. So that's how, procedures in the code also remains live. You know, uh, it allows this kind of changes. Same thing with the changes with FRP. Initially, there was no design code, but by allowing construction in a limited scale and monitoring and analyzing the monitoring data helped them to develop different design provisions. So this is another bridge in. So this was in Eastern Canada. Now this is in Western Canada in Calgary. So this is also another bridge constructed with similar concept, but with little bit of modification in the design. But here, the first one was simply supported bridge. This is a continuous bridge, and they did vibration monitoring almost every year for first few years. Okay, uh, these are some details. So, and based on those vibration data, there was some study to build, model updating, model updating algorithms, damage detection algorithms, because you have field data. So any algorithm you do, you have a perfect chance to validate those algorithms, right? So these are some of the simulation studies based on that. Then another bridge, again in extreme west of Canada, called British Columbia. BC is British Columbia. The biggest city there is Vancouver. So near that there was a bridge. It's a continuous three-span bridge. So these columns are longer and these are shorter. Now, in the earthquakes, when there is a lateral vibration, these columns undergo different kind of problem. Shorter columns are subjected to excessive shear. Longer columns have tendency to develop flexural hinges. So they wanted to update these columns, or upgrade rather, using FRP wraps. So FRP wraps means the columns are wrapped. So typically they scrape the columns, remove the cover, smoothen it, and then wrap it with FRP sheets, and then put the new cover. So what is the advantage of that? Advantage of that is that it confines the core of the column. Now, through different tests, it is always figured out, quite well known, that if you confine a column, its axial load carrying capacity goes up. If it is a longer column, if the confinement is done properly in the hinging zone or the end zone, then it behaves in a more ductile fashion, because the concrete remains in one place, the steel gets enough strain limit to yield and generate full hinge. This is there. See, this was in 2002 or 2003 period. They had this online monitoring system where they could access, process the data from a remote location. So there was a network of centers of excellence in Winnipeg. Winnipeg is in the middle of Canada. Canada is a very big country in terms of land mass, right? And it is a little bit longer. So it looks like this. So this is east, this is west. And If you take a flight from here to here, so this is Montreal and this is Vancouver, it takes 5 hours. So you can imagine how much longer it is. So Winnipeg is right in the middle. And they had this center of excellence where they had this monitoring station, and the bridge was in Vancouver. So it worked out well at that time. They also did field test from time to time, doing static load test. So they would run a truck with predefined load very slowly on the bridge, and then see what is the level of strain change, okay, in the in some of the girders. So they would measure this in each girder, and that will help them to find out what is the load sharing between the girders, because load sharing is an important aspect in bridge design, particularly when you design the multi-girder bridges. Okay, this is the Parliament building or Assembly building, let's call it, the Provincial Assembly building in Manitoba. Manitoba is the state, and Winnipeg is the capital. Winnipeg is where the center was. So this building had an iconic structure here. It's called Golden Boy, which is a statue which is perched on top of the building, connected here, and it is a bronze structure but plated with gold leaf. So at some point the government had some concern that maybe this connection is not working properly and this structure might dislodge from here, and that will be a major issue. So they asked the center, ISIS Canada Research Center, to investigate it. So when they looked at it, they found the connecting shaft was corroded. So then obviously a consulting company came into the project and did sort of replace that structure which connects this statue. And at that time, the structure was instrumented. Now, the reason why this project was significant is this is one of the very early SHM applications in Canada. Okay, SHM in the modern sense, like using fiber optic sensors, wireless sensors, and those kind of things. So these are some details of the structure, and then they monitored the structures for more than 5-6 years to ascertain that all the repair works were in good shape. They correlated with wind, correlated with regular ambient vibration, and all kind of things. And that is the time they started applying fiber optic sensors in civil engineering structures. That time, fiber optic sensors were not very popular. They were very expensive, and it was not very well tested. So these are some of the early pictures from there. Okay. They also tried to create something called rugged version of FOS, fiber optic sensors, because fiber optic sensors are very fragile. So it is like a simple fiber and coated with, under different kind of jacketing mechanisms. So as long as it is protected within this plastic jackets, it is okay. But the sensor part is usually exposed, and they are very brittle. So that's why installing in the field is very, very tricky. If it is not installed properly, then it will not work. So all the expenses will go waste. So they tried different ruggedizing mechanism, means pre-install in a different setup and just plug in the site and all these things. Obviously, they needed to study its efficacy and performance. These are some of the tests they did in the lab. We also did something in our Concordia labs. Okay. And what we did also is weathering effect, because Canada is a country which sees extreme weather. Extreme weather means in summer season it is quite hot. It could be 35, 40 degree and sometimes, not all the time, sometimes. In winter time, it could see minus 20, minus 30 even. Okay. Uh, Not for extended period, but on a regular basis, but minus 15 to 20 would be almost regular. So in that kind of temperature variation, uh, we need to know whether this kind of sensing system, monitoring system will even work in outdoors. Okay. So there were some tests to figure out what are the durability of these kind of structures, sensors. And also in fatigue condition, like especially if you look at a bridge, it undergoes cyclic load. Like every time a truck passes, the bridge midspan deflects, and then truck goes away, it comes back. And because these are dynamic load, there is also some kind of vibration that happens followed by the passing truck. So because of that, it might set in some kind of fatigue, especially in reinforced concrete, not so much in FRP reinforced concrete. There could be significant effect on this kind of fatigue load. Steel bridges has more effect because steel is known for its fatigue problem. So the test indicate that yes, FRP in all kind of conditions, like in control conditions, wet and dry, fed outdoor means summer and winter, immersed in different kind of solutions, they perform quite well. So durability wise, FOS seem to be good. These are two different versions. One is directly installed. This is installed on a supplemental bar. And these are traditional sensors, electrical based, which sometimes work, sometimes do not work, especially if it is extreme condition. We also did some research on application of SHM system in large structures like dams. Now, in a massive structure, environmental and seasonal effect, changes or affects the outcome of the monitoring system quite drastically. So we need to figure out a way how to extract the environmental effect or how to isolate the environmental effect. So there are many different techniques. We could use statistical method or artificial neural network method to isolate the effects. Analytically, some people tried using different, the existing theories of thermal expansion, etc. But that could count for only temperature-related issues, but not with other things. So this graph basically shows that if this is the raw SHM data, say displacement output at the top of one of the points, okay, then if we can correlate with water level, we can correlate with temperature, we can correlate with season, different season, different kind of data, then it might allow us to look at the pattern and isolate the effect of different parameters. For example, seasonal effect seems to be the most predominant here. Why? Seasonal effect is also connected to temperature, right? So temperature variation straight away influences the outcome. Then water level has some effect. And also there are some effect, we call it irreversible effect. Irreversible effect means over year, if you look at 20-year period or 10-year period, we see a certain level of change. It's a downward change. That means the structure is degrading. Although it is slow, but it is definitely degrading. So this kind of monitoring gives us a good information in terms of the structure's operational behavior and what is the long-term drift in its performance. This is an iconic bridge in Canada. It's in Eastern Canada. It's called PEI Bridge. PEI is called Prince Edward Island. It's an island in the east of Canada, which is around 13 kilometers away from the mainland. So the only mode of communication was ferries. But then in around 97 or so, they constructed this bridge connecting mainland to this island. So it's called Confederation Bridge. And this bridge, some of the critical spans are instrumented for long-term monitoring. Now, long-term monitoring helped maintenance of this bridge in a big way, because this bridge, when it was constructed, many of the things they didn't know. They assumed that this is how the bridge will behave, or the environment will react to the bridge in certain ways. So they devised solutions in anticipation. But since they monitored, they could now validate or update, say in the winter time, parts of this ocean, this is ocean, part of the ocean freezes around this. And some of the areas, it may freeze, but not fully freeze. So the ice blocks will move along this. Okay. So when it moves, you see these piers, it will hit the piers. So they had to account for that also. Okay. That what is the deterioration that can happen because of moving ice flow. Okay. And so with so many years of monitoring, they changed the mechanism to deflect the ice few times, just based on the monitoring data. And also they monitor the vibration patterns of this bridge quite regularly, because this is in the open ocean and the wind load is very high. So the bridge sways with the wind quite significantly. So this is a schematic diagram with some of the sensor positions. I'll not go too much into details of this, but we developed a model called statistical pattern recognition model. So based on the data, we tried to figure out if there is any malfunctioning sensors. Because when you get sensor data, you won't know whether the data is right or wrong, right? And if the data is not right, whatever analysis you do with that, it may not be very useful. So based on the technique is basically tries to isolate based on the pattern. Say we have a structure, a bridge, let's say, and we have sensors at different points. So when this bridge deflects, these sensors will give us corresponding information, right? Now, suppose out of these three sensors, this one gives different output, then obviously visually we can say that something is wrong, either with the sensors or at the location of the bridge. Now, if the bridge is an elastic structure, even if there is damage, post-damage version will also be sort of elastic, right? If the sensors are connected to that, maybe overall deflection will change, but not one sensor giving abruptly different result. So from that, you can figure out that maybe if this sensors is giving this kind of information, then there might be something wrong with the sensor. Okay. But if it gives excessive deformation, but on it with the same pattern, then it may be structural damage. Okay. So it is easy to do with limited number of sensors or simple structure. But for a complex structure with many sensors, we cannot do that. So we need to use some kind of pattern recognition technique to figure out which sensor is responsible for abnormal data. This is another iconic bridge in Montreal. So Montreal has a major river called St. Lawrence River. So St. Lawrence River is like Ganga of Canada. It is one of the major rivers in Canada. It's very wide. It's almost like 3 kilometers, not three, even more, around 5 kilometers wide at some points. So this bridge connects the two shores of St. Lawrence River. One side is Montreal, another side is other part of Quebec called South Shore. So you see behind there is another bridge here. This is the old bridge. So it ran out of its life. So, and the new bridge was constructed. And the new bridge, I think construction took about 2 to 3 years. But they discovered that they needed to construct this new bridge 10 years ago. Okay. And then approved the project, approved the money, design was done, and finally construction was done. Whole process took 10 years. So what would happen to the old bridge in these 10 years? They monitored that old bridge heavily and made sure that it will perform during this time until the new bridge is constructed. And the new bridge is also monitored and instrumented for long term. Okay, the instrument for temperature, expansion joint, wind, traffic, deflection in different spans, acceleration, and the cable forces, because this is a cable stayed bridge. The company that manages this bridge, they are very tight-lipped about this monitoring data. So they only give the overview information, not too much. But all I know is that I got some access in a limited scale. From that, I know the bridge is doing very well. This is a new bridge, so expected to do well. Also, they monitor the snow load. And this bridge carries different kind of traffic and also railway. Not rail, full rail, it's called light rail, right? A tram system. We also did some tests on our campus buildings for vibration using type of integrated sensor called, it integrates accelerometer, velocity meter, which is essentially a geophone, all this in order to, and also special circuitry to amplify the low amplitude vibration, because sometimes when you measure ambient vibration amplitude is very low, so sometimes the data integrity is compromised, right? Or the noise kills part of the data. So there is inherent sort of hardware level amplification of the vibration data. So from that, we use different system identification method to calculate the frequencies and the mode shapes. Okay. We, since this is done on the first time, the only way to verify is the finite element model. Okay. So other way to do it is repeatedly measure it, see that there is a consistency among the results. Now this is a snapshot of the activities here. There are many other projects. I know it's not important to bring everything, just to give some snapshot. But what is important to recognize, what are the challenges in these kind of projects? Some of the challenges were recognized early on and they tried to mitigate. Some of the challenges are still being recognized. But one of the, some of the major challenges that were recognized early on is optimal selection of sensor type and placement. That means if I want to monitor a structure, what kind of sensors I need and what kind of parameters I need to monitor and where we'll place this sensor. Okay. If I have a damage type and location well known, then I have no problem. I can select the appropriate type of sensor, location is known, that's okay. But generally speaking, we don't know many a times because the overall structure looks good or bad, okay? But to monitor it in a scientific way, we need to find a mechanism to install the appropriate type of sensors in appropriate locations. So I think that can be done with modeling, simulation to know the structure well before we decide that these are the critical points where the sensors needs to be installed. Also, installation in the field is very critical. Many a times we just rely on the consultants that this is what we need to do, install the sensors in these locations, and we collect data. But if they are not well trained and if the installation was not done properly, whatever we get is not very useful. So that's where multidisciplinary cooperation is necessary. Civil, electrical, even mechanical, computer science, background, professionals are needed to collaborate to develop a good SHM project. Okay. Then there is issue of measurement errors. As I said, if the amplitude is low, the effect of errors will be higher because any electrical or optical equipment will have some error. Optical equipment will have less error than the electrical systems. Wireless system will have error. So if you are measuring something, say you are measuring acceleration, typically there will be a random signal, right? If the error quantity in the random signal is lower, say error is like this, and the signal is this, then signal to noise ratio will be high. Then we don't have to worry too much about it. But if our original vibration signal, if it is low amplitude and original vibration signal itself is like this, which is close to our error, then we have trouble, right? So we have to find different ways to isolate these errors, mitigate the sources, remove the sources of errors and mitigate its bad effect. Another issue is environmental effect, which I already discussed, is that there is in a regular structure, there is always temperature variation, there is excessive moisture content, if there is rainy season, dry season, that can affect the data. And we need to find a mechanism to isolate those effects. Luckily, there are many methods developed by now, but there are issues. Correlation of analytical model to actual structure. This is extremely important because many a times we don't have all the data to evaluate a structure. So we need to develop a mathematical model or finite element model. So if we don't assure that mathematical model is true representation or close representation of our real structure, then anything we do with it will not be very useful. And as I said, data interpretation is the domain or area where less attention is given so far, okay, from SHM communities. We focus more on instrumentation, data collections, and things like that. But data interpretation is very, very important, okay, to finally assess what is the condition of the structure, okay, not just damage, not just local defects. What is the overall condition of the structure? And what is the remaining service life of the structure? That is very important. How to use SHM information? We can use in different system. In bridge management system, it is related to bridge. Dam safety assessment system, if it is related to dam, and so on. Data fusion is often a necessary thing. Data fusion means you have different kind of data, like inspection data, vibration data, strain gauge data, all kind of data with different kind of ranges and their behavior. How do we fuse all this information to interpret the data appropriately? And the final objective is this: condition assessment and prediction of remaining service life. Many a times we can use this as life cycle assessment, not just costing, I would say assessment. So what does it mean? You have a bridge built for 60 years, but at the end of 40 years, you see problems, right? So if you demolish the bridge at this point and reconstruct, it will cost some money. But if you can, through SHM, if you can extend it to really 60 or 70 years and then construct, then it has a different cost. Let's say reconstruct here, so it has C1, and reconstruct here, it has C2. Then you compare on a yearly basis which one is cheaper. You will always find that this is cheaper. Okay. So that gives a justification of extending the life. Okay. So this is, and real-time assessment or continuous assessment is always helpful. I'm almost done. I would acknowledge my colleagues, workers, all my graduate students who helped me over the years to do different projects, different research initiatives, etc. These are some of the funding agencies in Canada. NSERC, which is one of the main funding agency, called Natural Sciences and Engineering Research Council. FRQNT in Quebec. IC Impacts is a network of centers of excellence which promoted Canada-India collaborative research in collaboration with DST or IBT. DST in India. IBT is also in India. It's biotechnology, I think Department of Biotechnology. I also got Spark Fellowship few times, so I acknowledge their support. ISIS Canada Network, some of my colleagues, and industrial partners. With this, I want to stop here. Thank you. Maple leaf is Canada's symbol. Maple trees are everywhere, and in the fall term, it turns beautiful reddish yellow colors. So thank you very much. If you have any questions, we can take them now.
So thank you very much, Professor Bagchi. It was really a very eye-opening lecture because you covered a lot of real-life case studies from Canada. So I hope it must be very, very useful to all the attendees. So now we have few questions we can take up. So first, the hand is raised by Dr. Sushil Dhawan.
Uh, Professor Bakchi, excellent presentation. We could
Thank
listen
you.
the actual variation of season and environmental effect. Actually, the temperature going from 30 degrees Celsius to minus 30 degrees Celsius in the
Yes.
period. And the structure is existing at least, say, as you said, 100 years. The thing that as a structure in here, we see the stiffness, mass, frequency, and damping effect. Now you
Yeah.
have put sensors at various places, the type of sensors you said,
Yeah.
accelerometer and other type of sensors. See, my first question is that we know the baseline that this is a safe structure.
Mm.
Now the structure line is say 100 years with so much variation of temperature, weathering effect, environmental effect.
Yeah.
Uh, and the life of sensor, the life of service life of project, say, for 100 years.
Mm.
Now, taking data, processing data, what mechanism you have there in your country to see that the data is kept well and monitored for 100 years, and the life of sensors, the type of
Yeah.
sensor that you're using.
Yeah.
Please just highlight these two, three things
Yeah.
which are.
No, this is an excellent observation, excellent question. This is one of the challenges. If we build a structure to last for 100 years, we haven't built sensors to last for 100 years.
Right.
Okay. So if you take traditional sensors, which are operated based on electronics,
Mm-hmm.
they in outdoor environment, even if you protect them very well, they don't last longer than 5 to 6 years.
Mm-hmm.
Okay. Now that's why for long-term monitoring, fiber optic sensors became popular.
Mm-hmm.
Okay. Because they say that if you install, the trick in fiber optic sensors is the installation, because many a
Mm-hmm.
times it breaks during installation.
Mm-hmm.
So if you install properly, then it can live 100 years. Okay, because optical fiber hardly degrades. We tested with all different adverse conditions and it performed well. So the expectation is that if we internally, if it is concrete structure, we can install them internally. Once it is installed properly, it remains protected and it lives with the structure. Okay. But we may not, at the time the structure was constructed, maybe not adequate fiber optic sensors were installed, or it might not have come to anybody's mind to put fiber optic sensors at that time. What do we do with them, with those structures? We have to install sensors externally. Even then, fiber optic sensors works well, even if you install externally. But the electrical sensors has the advantage is that they are relatively cheaper. And if you need to replace them, you can replace them every 5 years, okay, or depending on the cycle. Or they are very good for periodic monitoring, like vibration test I mentioned. If you need to do vibration test every 6 months, you carry all the equipments, install it temporarily, do the test, and bring the sensors back. So that way, if the structure is expected to last longer, then the monitoring regime should also be longer. What way we do, whether periodic, continuous, or anything. Because if we don't do it for longer term, we do only when we think that, oh, structure is in bad shape. This is the good time to monitor. By that time, the structure is already in bad shape,
Right.
right? So if we monitor in the early stages, that gives us the baseline, so that when it is in bad shape, we know how bad it is. So otherwise, we have to compare one bad step to another bad stage. So that's what we are doing with most of the old structure.
Now, the final second question, just as a layman, in your country, of course, you are in Canada for last many years, the bridge management system over there,
Yeah.
just the border things that are seen there in the bridge management system. Just few important things that
Yeah.
are
So
these.
what do we do in terms of bridge management system? Is that your question?
Yes, yes, please.
Yeah. So almost all, and see, Canada has different provinces, and transportation system comes under the province's jurisdiction, unless a bridge is crossing different provinces or crossing international boundary. Then it becomes the federal government's thing, or the central government here. So, but all the provinces have adopted some kind of bridge management system on their own. Okay. And in US, it's the same story. They have a national bridge management system and provincial bridge management system. So what do? It's basically they collect all the information about the bridge and put it in the bridge management system, which is a huge database, I would say, with the capability to do some analysis. So in the US, they have national bridge inventory, and also the provinces collect all the data and put in that national bridge inventory. In Canada, we don't have a national bridge inventory, but all the provinces keep their own data, okay, and manage the bridges accordingly. So there is a major company called Stantec who who has who has a robust bridge management system. They developed the system, and most of the provinces here in Canada uses their system, and many of them in the US use their system. Okay, customized to different provinces based on their needs. So that's how they are doing.
Right. Thank you.
You're welcome.
Okay, so next question, Dr. Naveed Kaur.
Hello, Professor Bagchi. This is Naveed. I'm working as a senior scientist in Central Road Research Institute in New Delhi. So, my question is in continuation with the Dr. Dhawan. You were mentioning about the vibration test. So, I was just curious whether you do the vibration test under the moving traffic, or you generate with some hit hammer, or how do you do the
It depends on the structure, really. So if you do a test in the lab, for example, a building frame, for example, it is not difficult to excite the structure with an impact hammer or some kind of low duty shakers, right? And collect all the vibration signals and analyze the data to extract the model properties. But if you go to a real bridge, it is very difficult to shake the massive structure on your own, or with this kind of devices. So, but traffic load creates vibration, right? So you can rely on that vibration, which is not perfectly ambient, but it is generated externally by somebody else, not by the person testing, right?
Mhm.
So our objective is to capture free vibration signal because that is what gives us the model properties, right? So if a truck passes at high speed,
Okay.
the bridge still keeps vibrating, although we may not realize, but it still keeps vibrating. And that data could be used for your system identification.
So it means you're telling that we will get some kind of damping response, and rather than taking the whole response, starting from the highest peak and then reducing slowly with the time, we should rather take the end, the damped response at the end of the structure. Is it what you're telling?
Well, I look at it this way. Every civil engineering structure has damping. In fact, any mechanical structure has damping, right?
Mm-hmm.
You cannot get rid of it.
Mm-hmm.
You should not,
Mm-hmm.
right? So when it is forced vibration,
Mm-hmm.
the effect of damping is not apparent, right? But when it goes into free vibration response,
Mm-hmm.
the response gradually dies down, right? So you can capture the whole signal, doesn't matter. But essentially, you have to isolate the forced vibration part because forced vibration part has two things mixed into it. One is the characteristics of the external load and characteristics of the structure, right? We are not interested in characteristics of the external load at this point. We want to know the system properties of the structure, right? So that's why we focus on the free vibration response,
Uh,
which has damping. So it allows us to estimate modal frequencies, mode shapes, as well as damping.
Can you, do you mind putting that response in the slide like the way you were doing with the pen and help me understand that what I should be considering? How to differentiate the forced response and the uh, free in the slide?
Okay, so let's say this is our acceleration versus time, all right?
Mm-hmm.
And you get some signal.
Mm-hmm.
This part is say forced vibration part. This is free vibration part. I don't know which one is what. That's what you are saying, right?
Yeah, yes.
So, but if you do frequency analysis of this, you will get, different kind of frequency contents for this as
Yes.
compared to this, right?
Yes.
So many a times what we do is that, if you take a busy bridge, all the time traffic is passing. So if you wait for free vibration, maybe you have to wait too long. So
Mm,
you take the signals in a way
okay.
and divide into different time windows,
Okay.
okay, and do the analysis, extract the frequencies based on that. Many a times we try to do, you know, um, singular value decomposition or things like that, that will take out the noise or unusual characteristics from the vibration data. Okay. And then you will get different ranges of frequencies from different time windows. You see which kind of frequencies are repeating in different time windows. Okay. Most likely that will be related to your structure.
Okay. Repeating frequencies.
Repeating pattern in different, say you may have 5 different modes you capture from the signals, right? Let's say. So 5 modes will be related to 5 frequencies. If you see that in different time windows, these 5 frequencies are repeating.
Ah, okay.
So that will be mostly related to your free vibration.
Got that. Got that.
Okay.
Yeah.
This is just for frequency. For extracting the damping, there is a different process.
Yeah, I understood. Thank you. Thank you so much. One more question. This
Okay.
dynamic response, how much is it sensitive to the damage? Because you were telling that this you have used for detecting the distress in the structure as
Yeah.
well. Is it
Yeah.
really sensitive?
I would say if there are it depends on the type and location of the damage, but mostly it is not very sensitive.
Hmm.
Okay. So if you just look at the frequencies and mode shapes
Mhm.
of damaged and undamaged structure, you won't find too much difference. So that's why researchers always discourage comparing them directly.
Hmm.
Okay, so you have to use different methods to amplify these differences so that you can detect the damage. I'll give you a simple example. If you look at the mode shape, so I'll go back to the slide again. If you take a simply supported beam and let's say this is your first mode shape,
Mhm.
mode 1. This is undamaged. Then after, suppose you inflict a damage manually, you create some damage yourself somewhere here,
Mhm.
and your mode shape becomes like this.
Hmm.
If you compare them directly, you will get this kind of difference, right?
Yeah.
Which doesn't tell you anything,
Mhm.
which does not tell you about the extent of damage and the
Location of
location
them.
of damage or anything, right?
Hmm.
So then perhaps you can look at the curvature of this
Mhm.
mode shape,
Right.
okay, and plot that curvature difference. That might indicate some kind of, you know, changes here.
Hmm.
Depending on cases, again, it may not be always true, but in some cases it will show some indication that there is some change in the curvature. Now, why is it so? Because curvature, if this is the deflected shape y, curvature depends on y double prime,
Hmm.
right? So double derivative of the displacement.
Hmm.
So when you do that, you amplify the effect, right? So the differences become higher.
Right.
So like that, there are many other methods to see how we can use vibration data to detect damage.
Understood. Professor Bakshi, actually, we are working on. We got some project of checking the condition of 200 bridges, 200 structures rather
Okay.
on an expressway in NCR. So from Greater Noida to Agra, that is there.
Okay. Excellent.
So yeah, thank you.
That's a big opportunity.
Yeah, thank you so much. So
Yeah.
actually, since we got this opportunity, so we thought of doing one study to measure the natural frequency of the different type of structures. Of course, the
Yeah.
structures are not really of very long spans as such. But
Mhm.
since the type of structure is varying and little bit spans are also varying, so whatever
Mhm.
different type of structures I could find from that particular list, we have identified, and then we'll do the dynamic response testing for those structures. Now, for that,
Okay.
I'm trying to understand all these questions. And one more
Mhm.
thing which I have in my mind, when we are taking the readings, say in one carriage weight, we have 5 to 6 girders, for example. Then is it sufficient I put the sensor on any of the girder one location and take the dynamic response of the whole structure, or shall I maybe say take the readings at 3 to 4 locations along the carriage width at the mid?
I think you should instrument it as, as widely as possible.
Oh,
But of course, as I said, optimal sensor location is very tricky to find, right?
even
So
for
you
the
need to do some kind of preliminary structural analysis to know
okay.
where you will have the nodes. Nodes means zero displacement when it vibrates,
Mhm.
and where we will have higher displacement when it vibrates. Typically we put the instruments at the locations where we expect higher displacements.
Yeah, along the width also.
Along and also across the bridge, you should instrument is as widely as possible.
Yeah, because say we are planning to use the accelerometer single or maybe 2 or 3 sensors at mid of the span and along the carriage width, maybe 3 locations. Is that good or not?
Well, if you are only focusing on mid-span, then you are planning to capture only one mode,
Yeah, right now
right?
the idea is to capture one mode only and prepare a data
Okay, then
bank,
then it's fine. Then it's fine.
because the higher modes is another thing which I believe is not really sensitive also. So even if we capture
Well, for most of the design and evaluation process, the fundamental mode is
sufficient.
considered.
Hmm.
But if you really want to do structural condition assessment and damage detection, then you need multiple modes.
Yeah, but the spans of the bridges are not really big. So maximum span is 25 meters for all the
Okay,
structures.
then probably one mode is fine.
Yeah. And many a times it is a box type structure also. I don't know
Yeah.
what I will get out of it, but we are just taking the readings just to prepare a data bank, since something like that is
Okay.
not existing as such.
Okay. That Yeah, it would be interesting to see what so many bridges tell you. Yeah.
Okay. Thank you so much.
Thank you.
It was really insightful.
Actually, what I'll do, I'll leave my uh, email ID here.
Yeah.
So it's clear, ashutosh.bakchi
Yeah.
at concordia.ca. So if you have any queries later on, you can
Sure.
email me.
Thank you. Thank you so much. It was really insightful.
So
Thank,
we thank Professor Bagchi for a very insightful lecture,
thank you
and
very
he was
much.
you have been very patient with the questions. So I hope all the audience, everyone must have learned really the lessons, because Professor Bagchi covered very detailed studies right from the beginning of the SHM process in Canada. So with this, I think we end our session with a note of, again, thanks to Professor Bagchi. So all those
Thank
who
you
are
very much.
attending,
It was my pleasure, and I might be back to India in summer sometimes. I'll get in touch with you, and it is my great pleasure to meet all of you. Thank you
thank
very
you,
much.
thank you,
I'll
thank you,
sign off now. Take
thank
care.
you, thank you. So all those who
Bye-bye.
are attending this talk for the first time, we hold such talks every month. And if you want to join the Indian Society, Indian Structural Health Monitoring Society, you can just Google it, and you can just go to the website and fill up the application form. Thank you very much.